Here we're going to be looking at exponential functions basically in real-world settings. Okay, and so what we're going to do is we're going to say, how do we write an exponential function to model each, or to model maybe a real-world phenomena? Okay, because we use functions to model this so that we can predict future outcomes and things like that. So let's look at the concept of exponential growth and decay, which we've talked about in class, when applied to word problems, normally involve the quantity growing or decaying, because we've talked about a growth function and a decay. Now the key here is this constant percentage over time, typically. Now exponential growth, okay, which we've discussed, focuses typically on population, financial investments, biological entities growing in size. Okay, then we have decay, exponential decay. This is often found in diminishing price of a product, such as yearly loss of value of a car, which is called depreciation. Okay, so depreciation, steady decrease in population, or radioactive decay is common. This is of isotopes. So these are some common applications for exponential modeling that we can use. Now let's look at an example of where we would use this. Alright, suppose that acreage of a forest is decreasing by 2%. Alright, first of all, here's the key concept, decreasing. So we're going to end up with a decay here by 2% per year. And per year, okay, so that's constant because of development. If there are currently 4,500,000 acres of forest, write a function to model the real-world phenomena and determine the amount of forest left after each year. Alright, so let's go ahead and come up with a model for the function. Alright, now remember that for a decay function, exponential decay function, we're going to end up taking the form f of x is equal to a bx. Now, remember, f of x is the same as y. When we write this, we're basically telling everybody that we know it's a function. So we're going to use functional notation for this right now. But we could replace that with y. But anyway, so a, b, x. Now remember, a has to be greater than 0, okay, and that b has to be between 0 and 1. Okay, so now we refer to the b, or the base, as our decay factor. Now for this particular problem, our function would end up being our a value, which is what we started out with. Okay, so our a value is this. Now this would be a good time to use scientific notation because we have all these zeros. So let's go ahead and do that. So we go 1, 2, 3, 1, 2, 3. So we have a total of 6. So we can write this as 4.5 times 10 to the 6th power. So that's an example of when we would actually use scientific notation. Now, the base, okay, is where we have to be careful here. Now, for decay, it's got to be between 0 and 1. The temptation may be to put 2% in there, okay, but what we're going to end up doing is taking 1 minus 0.02. Now, where did I come up with the 0.02? I converted the percentage to a decimal, and so we just moved the two places over, so we get 0.02. Okay, now that's going to be the t power, because that's our time in years. Okay, and so what I'm going to do is clean this up again, so a little bit. So we have f of x is equal to 4.5 times 10 to the 6th. Okay, 1 minus 0.02 gives us 0.98 t. So 0.98 is going to be our base, or our decay factor. So if I ask you what the decay factor is, in this case, the decay factor is the 0.98. Alright, so but for our model, that's our model. Now we really didn't have to put this in scientific notation, but it makes it easier to carry that. Now, so we came up with our model. So that means for any year that we put, for however many years we can get a good estimate or a good idea of what's going on with our population of the forest. Now, to use this for part A, what we would simply do is take our function 4.5 times 10 to the 6th, and we're going to take 0.98 to the 3 years, so that's going to be our power, our exponent. Okay, and we plug that into the calculator, and that'll help come up with an answer for this particular one. Alright, once we plug all that in the calculator, this is what we should end up with. Now, for this one, there's really no point in scientific notation because we don't have a lot of zeros. So, after 3 years, okay, our forest has decreased to 4,235,364. Okay, now let's look at 5 years. Now, if we did 5 years, everything else would stay the same. The only difference is we plug in a different value for our t. So we're going to raise it to the 5th power. Alright, and so what we see here is we get f of x is equal to this. Okay, so that's our f of x value. Now, what I want you to do is go ahead and try 10 years and 20 years and see what you come up with. Now, I'm going to write out the function. Remember that time is the only thing that's changing for us. Alright, so here are our answers for after 10 years. This is how much of the forest is left, or how many acres of the forest is left. And then after 20 years, there's this much left of the forest. Now, it may be helpful to put in some commas to kind of break it up. So you can see that we're having a decay because the amount is decreasing. Okay, and again, it's a decay if we just look back up here at our decay factor, which is our base, which is underneath the exponent. Okay, and so that's how we would use this.